Okay, in today's class, we discuss limited and excess reactants. A quick recap of the concept. So during chemical reactions, reactants are at times all used up or left over. They're not always given to us in perfect proportions, like a balanced equation would maybe predict. So we know the problem is a limiting reactant type problem when we're given amounts of more than one reactant. We'll see these in the examples that come up. When you're given a limiting reactant problem, I want you to follow these steps. First, convert the amounts of the reactant, this could be grams or it could be moles, to the product. And maybe you convert it to the question that's being asked. If it's asking for moles, go to moles. If it's asking for grams, go to grams. Now, once you've done that work, the answer to the question, how much product is made, is always the lesser of these two values. This just means that the amounts of one of the reactants ran out such that we can't make any more product. As we kind of saw in class, once you run out of marshmallows, you can't make any more s'mores. Now, the reactant that led to that lesser value is the limiting reactant, and the reactant that led to the greater value is the excess reactant. Now, oftentimes after doing this work, you're done. But sometimes it says, and it asks, how much of the excess is actually left over? So when this question comes up, I want you to do two more things. First, I want you to convert the product that was made to the excess used. And again, we'll practice that in a minute here. Then, this does not answer the question, how much is left over, how much is used. It's a different piece of information here. So to finish this problem off, you would always have to subtract the excess used from the excess that the problem gave us, or that initial value. So now let's look at some examples. When butane is burned in gas grills, butane is C4H10. I keep on doing that, H10. It reacts with oxygen gas to produce carbon dioxide and water. Now, this is one of those CHO type problems, so I hope that soon we're able to predict that the products are CO2 and water, although it just told us they were today. Now, to balance this equation, I would say I have 4 carbons on the reactant side, so let's get a 4 on the product side. I have 10 hydrogens on the reactant side, so 5 times 2 is 10 on the product side. Now, oxygens on the product side, I have 4 times 2, which is 8, plus 5, which is 13, and 6.5 times 2 is 13. Now, especially for my gold class, I think I rounded this to 7, and we were supposed to fix it, actually, and we didn't get back to that. To address this 0.5 now, I would double everything. So I get 2 butanes, I get 13 oxygens, we have 8 CO2s, and we have 10 waters. So this means that for every 2 moles of butane and 13 moles of oxygen, we get 8 moles of carbon dioxide and 10 moles of water. Now the question says, if 100 grams of butane is burned with 100 grams of oxygen, how much CO2 is produced? So let's go from both of our reactants, 100 grams of butane, to product, grams of CO2. This is a 3-step problem. We're going to start with the molar mass of the given on the bottom. We're going to next use the balanced equation ratios, which is 2 moles of C4H10 per 8 moles of CO2. And then 1 mole of CO2 is 44.01 grams of CO2. Okay, we do this work and we get about 302.7 grams of CO2. Now let's do the same thing for my oxygen. So I have 100 grams of O2, and we're also looking for how much carbon dioxide could be made. So oxygen has a molar mass of 32 grams per 1 mole. We have 13 moles of O2 per 8 moles of CO2. And then 1 mole of CO2 is 44.01 grams of CO2. And this is 84.63 grams of CO2. So remember, for the first question, how much is made, the product made is just the lesser of those two values. So we've done the work. Let's just circle the lesser value. That's how much is made. Now, if you were to be asked which of the reactants was limiting, make sure we're not answering carbon dioxide. It's not a reactant, that's a product here. So the oxygen led to that lesser value, so the oxygen is limiting. The butane led to that greater value, so the butane would be left over. Now, here is that last final question. How much of that excess reactant is left over? Let's start from the product made, 84.63 grams of CO2. And let's go to excess butane. Now we have 44 grams of CO2 per 1 mole of CO2. We have 8 moles of CO2 per 2 moles of butane. And 1 mole of butane, again, was that 58.11 grams of butane. I'm kind of run out of room here. Okay, so we do 84.63. We divide it by 44.01. We multiply by 2. We divide by 8. We multiply by 58.11. And we get 27.95 grams of butane. Now, we're not done because this question asks for how much is left over. And this is how much is used. So don't forget, and this is the most common thing, is forgetting to do this last step here, that we always then subtract the excess used from the excess initial. Now we started with 100 grams of butane, and we used up 27.95 grams of it. So I think we get 72.95 grams left over, and when we're doing addition subtraction here, we would go with that fewest decimal, so I would just probably round that to 72.05. So I just round it to 72, maybe 0.1 even though it's 72.05. 72.05 grams of the butane would then be left over. So I'm going to make another video for the second series, so I have a little more time to go through it. So I hope that was a nice little recap of what is a limiting reactant, what is an excess reactant, and how we go about solving these types of problems.